Hello everyone, I hope you're doing well and being safe. This is the first lecture I'm recording for you for mechanics and heat. We were supposed to meet 3 weeks before, but you know the situation. So I'm gonna try to record my lectures for you and send them to you through YouTube or WhatsApp. What I'm gonna do is I'm gonna post the lectures on YouTube and send you the link. I will also send you the lectures as PDF. I already gave you the book, so today I'm just gonna cover general stuff and a little bit of a review from chapter 1. Our first real lecture will cover chapter 2 about motion. First, what is the course that we are discussing? As you see from the name, it's called Mechanics and Heat. So in the first part of the course, we're going to learn about motion, how to describe motion. Then we're going to discuss Newton's law, how to predict motion and why we have motion. Then we're going to cover the concept of energy and momentum. And hopefully, if we have time, since we're doing this online, so we should have time, and we should cover thermal and heat energy. The textbook is Essential College Physics, and I already sent you the link for that book. The lectures and homeworks I will post on my website that you saw the name before, and I will also send them to you as WhatsApp, and I will put the videos on YouTube. Usually in this course I ask students to do a project where we design and prepare an experiment, a physics experiment that we can solve the equations for, and we prepare it together. Let's see how that is going to work. Let's see how the lectures are going to go first. Maybe I will ask you to prepare a presentation that you would share with us. Something to keep you busy. I think one of the advantages of studying online in these times is just to keep busy a little bit. Maybe we stay sane a little bit. For succeeding in this course, of course, these are kind of recycled stuff. Here our experience is going to be totally new. This is mainly the first time I record a full lectures. I tried it before, but not as extensive as now. Of course, you have the book, so read the book. There's a lot of problems in the book. I would also send you periodically the solution, the full solution for the problems in the book. Solve the problems firsthand. I will assign homeworks for you, and then after I assign the homeworks, I will give you, for example, a week to solve the problems. Maybe I will collect them from you as pictures on YouTube, or I will teach you how to scan them and send them to me. And then I will send you the solutions from the book, and I will try to make demonstrations of solving some of these problems on the board or something, and then of course share them with you. Ask me questions, because this is a new experience. Again, ask me questions on WhatsApp as voice or anytime you want, and practice problems as we go. What I'm gonna do is we're gonna do each week a lecture, so one lecture per week. Of course, the lecture is not gonna be 1 hour and a half. It's gonna be a short lecture, so you can watch it anytime. We'll see how this progress would go. If you're cooperative, maybe I will do 2 lectures per week. That way we can cover more material in short time. Of course, since we're not in class, I can talk much faster, so you could repeat the lecture as much as you want. So that's why they would be shorter lectures. Today in this lecture, I want to do some review about measurements in physics, and what units and how to use units in physics and in science in general. So this is the first chapter in the book. So if you read the first chapter in the book, it's called Measurements in Physics. Okay, what is measurement and what is units, a standard units system? So if you Google the unit of measurement, or unit on Google, you're gonna get the first link you're gonna get is from Expedia, and you would see the unit of measurement is defined as a magnitude of a physical quantity, defined and adopted by convention or by law, that is used as a standard for measurement of the same physical quantity. So what does that mean? It means that whenever we measure a physical quantity, in life we have what we call physical quantities, is stuff that we can measure. So whenever we have to measure these stuff, we have to agree, or we have to have a convention of a unit to use to understand what this quantity means. So for example, if I'm measuring time, time is a physical quantity. So if I tell you I slept for 8, what does that mean? It means that I slept a period of time. So I have to specify the unit that we both understand what this unit means. So if I say I slept 8 minutes, it's much different than if I say I slept 8 hours, since most what we're doing now in these days is sleeping. So any physical quantity should be related to a unit that is just we agree on to use. Now in science, there are what we call the International System of Units, SI unit system, that we agree on to use for different quantities. The fundamental quantities that they're gonna come up a lot in our course are distance, time, and mass. And for these quantities, we use meter, second, and kilogram. Those are the standard units. So usually we define the other units. For example, the unit of force is defined from these three units. Okay, the other thing that we need to understand other than the unit of the quantity is what we call the scientific notation. So a physical quantity is something that you can measure, but of course our measurements have a limitation of how accurate they are, and how we write these numbers should reflect for us how accurate our measurement is, because our laws, our physics laws, depend on the accuracy of the measurements that we can perform. So for example, if we are reporting the radius of the Earth is 6,371 meter. This is an approximate number. You see the zeros at the end, these three zeros, these what we call insignificant figures, because we are not sure if it is plus 1,000 or less than 1,000. So we have to be to reflect these in our numbers. So the best way to write a number is to write it in what we call the scientific notation. So the scientific notation, we leave only one digit before the decimal, and then we put all the other digits after the decimal, and we add a multiplier of a power 10. So we write it as 6.371 times 10 power 6 meters. So this number has four significant figures. The 6 is significant, 3 is significant, 7 is significant, the 1 is significant. These are the numbers that I am sure they are accurate in my measurement. And then all the zeros that I'm not sure of, I just removed them because they are after the decimal, and now they are clear that they are not significant. If we have numbers that are significant after the decimal, I have to keep them. The other way to write numbers is to use what we call the prefix, the SI prefix. So it's the thing that I add before the unit that is just a multiplier of 10. So for example, nano is 10 to the negative 9, milli is 10 to the negative 3, santi 10 to the negative 2, kilo is 10 power 3, mega is 10 power 6. So for example, for the radius of the Earth, I could have wrote it as 6,371 kilometers. So the 10 power 3, I removed it and I wrote instead kilo. So instead of meter, 10 power 3 meters, I have 10 power, kilometers. Now, if we compare that, for example, to the radius of the hydrogen atom, this is on the other end of the spectrum. It's a very, very small radius. So we wrote it as 1.1 times 10 to the negative 10 meters. So instead, I could write it in scientific notation as 0.11 nanometer. Or I could write it as 1.1 times 10 to the negative 10. Also, that's the scientific notation. So both notation reflect to me how accurate my measurement is. Okay, so in other areas of science and in everyday life, we might use units that other than the SI units. So for example, chemists would prefer to use the CGS system, where we have centimeter, grams, and seconds used instead of meters, kilogram, and seconds. For astronomers, it's easier to use light year to measure distance between stars. A light year is a distance that light would travel in 1 year. So it's not a unit of time, it's a unit of distance. We have to pay attention when you are using, when we are converting from one unit to another. The physical quantity doesn't change. What we are converting is the unit of the quantity, not the physical quantity. So from the unit alone, we can actually tell what is the physical quantity or how to calculate the physical quantity. So for example, if we see that this statement here, the density of gold is 19.3 gram per centimeter cube, we can directly tell that the density is mass over volume, because gram is a unit of mass and centimeter cube is distance cube, which is volume. So how do we convert the density, for example, to the standard units? So first we look at gram. 1 gram is 10 to the negative 3 kilograms. And we know that 1 centimeter is the 10 to the negative 2 meters. So each 1 centimeter cube, we have to cube all this, is 10 to the negative 6 meter cube. So what we do is we keep the ratio, and then we remove the gram, and instead of the gram, I put the 10 to the negative 3 kilogram. And in the denominator, I remove the centimeter cube, and I replace it by 10 to the negative 6 meter cube. So now I have the unit of kilogram per meter cube, and then I group the numbers, and I got 19.3 times 10 power 3, which I can leave it in that notation, or I can change it to the 1.93 in scientific notation, 10 to the negative, 10 to the 4, or I can write it as 19,300 kilogram per meter cube. Now, another things about unit is from the unit I can tell the dimension of the quantity, or what is related for. So the distance is length, time is t, mass is m, are the basic dimensions of mechanics. These are the basic quantities in mechanics. All other quantities that we're going to calculate or measure or define, they are basically related to these quantities. Of course, when we get to heat, we have to add one basic quantity, which is temperature. And when we get to electricity, we have charge or current as another basic quantity. But for mechanics, everything is related to length, time, and mass. So for example, speed is distance over time. So the dimensions of speed is length over time. And the standard unit for speed would be meter per second. Or we could measure it in kilometer per hour. Kilometer is a unit of time, distance, and hour is a unit of time. So kilometer per hour should give us time. Keeping track of the units and keeping track of the dimension would tell me if we have a mistake or not in our calculation. And it also actually would allow me to guess what formula to use for these quantities, even though if I don't remember the exact formula. So for example, if I tell you that the kinetic energy of a body, which is related to its distance, to how fast it's moving, has the dimensions of mass, length squared over time squared, I can actually deduce the formula that would give me the kinetic energy. So first, mass is the unit is the dimension of mass. It appears as power 1. So the kinetic energy is proportional to mass. Then I have length over time, but we have square on both of them. So that's velocity square. So I know that the kinetic energy is proportional to the mass over, mass times v squared. But actually I cannot tell any the constant in front of that. So in the real formula for kinetic energy, if you remember, is half mv squared, not mv squared. So the dimensional analysis tell me about the proportionality, but it doesn't tell me about these dimensionless factors that might exist. So it's a good tool to understand, but it's not sufficient to know the exact value for kinetic energy. Okay, this is as far as I want to cover from this chapter. There is a few more things in the chapter about accuracy and precision that I will leave them for now. We will talk about them a little bit as we solve problems and we will discuss experiments and understand more things about physics. Here are a few problems. They are from the book, so please read them. You can find them in the book. Try to solve them on your own. I will try to send you the solution later. Okay, hopefully this is going to be a good experience for all of us, for me as a teacher and for you as students. Please give me any comments you have about the sound, about the speed of the lectures, about the notes, anything that you see is relevant. and hopefully I will prepare the second lecture soon. Thank you.